Okay, great. Okay, and we can, yeah, we can have the tiny picture of me. Okay. Okay, so last time we were in class, we started going through Python syntax. If you're new to Python, I'd encourage you to go through this notebook and just make sure you have a sense of the syntax, because as you can guess, we're going to be using Python quite a bit in this course. And I think I still have my kernel running from last session, so I don't have to re-import. Oh yeah. Okay. Um, so we talked about this in the last few minutes of the last class, but I'm going to reiterate this because this is actually super useful and important, especially when we get to arrays and stuff. So notation for indexing into ordered objects in Python is very specific to Python. It's different than MATLAB. I think it's cool. I don't know, MATLAB people might feel differently. But the big difference is this colon operator is unique to the language. And there's very specific conventions where, 2 to 4 indexed into this array here returns, where am I? Yeah, this guy. Sorry, I really should label these as I go. So this is a little bit unintuitive that your first index is the first index in your callout statement actually points you to this inclusive, but the 4 actually cuts off before here. So you get 2 and 3, you don't get 2 through 4. That's just a convention of the language, but this will get you, right? This is a really easy mistake to make is, if you need to go up to 5. So just keep track of that and stuff. The other things are these partial completions where this says get me 2 through the end of the array if I have nothing there. Likewise, if I put nothing there, it's everything at the front of the array up to 4. And then this is just everything from the front to the back is how you should read that. And then the negative numbers are kind of fun, but basically just reverts everything to starting from the other end of the array. So start from the back of the array and go back an element, go back 3 elements, et cetera, et cetera. So this is just, syntax. It's not the most like conceptually interesting, but it's a nice thing to know because I'm going to be throwing around a lot of weird syntax when we get to vectorization. Okay, so I probably won't cover this because I don't think it's just something worth knowing. Another unique thing about Python is that instead of writing for loops, you'll see people write them in this compressed notation. So basically, this one-liner does the exact same thing as this loop here. It's nice just because it allows you to have slightly more concise code. So just you'll see me use that. And this definitely doesn't have an analog in MATLAB. So just keep an eye on that, especially if that's kind of weird. And then I will almost certainly not use map and filter in this course. But if you're a big fan of functional languages like Pascal or Mathematica or even R, you might be interested in learning about the map operator and the filter operator, which basically allow you to do functional programming in Python if that's like your favorite thing. Um, okay. Okay. And I'll go ahead and leave it at that on built-in types. And I'll just mention that all these things like integers, floats, lists, dictionaries, tuples, and then we didn't use sets because no one uses sets, but that's another built-in. All of those are what we call primitive data types. Every Python interpreter in the world has those. But the whole point of Python is that we're going to use this to build abstract data types. These are data types that are designed in the context of whatever you're doing, that are built from these native types, which have very specific properties. So if I'm building a numerical integrator, I might build an integrator data type. Python will treat that as if it's any other object it's encountered. However, everything about that object I'm going to specify rather than having its own properties like a float or an int or a more primitive type has. So primitive is built in, abstract is something that we build of the built-in. And that's the basic thing. And in the computer science, like in a computer science algorithms course, you'll spend an entire semester talking about different abstract data types and their different run times and all that. Um, yeah, I probably I won't get into it this much in this course. I'll just mention that data types, they seem like they're language specific, but you should oftentimes they sort of are language independent objects that you can represent in a language. So you should almost think of abstract data types as like mathematical entities that we choose to represent using Python or whatever. Um, okay. Yeah, and printing and string operations, we're going to use print statements. So just like maybe check out the syntax so you can use it. But none of this is that physicsy or anything. So just take a look at this if you want to use prints for stuff. And you'll see me use. I'm a real I don't know, I guess amateur programmer, I guess, because I use print statements to debug a lot. So if I have something where I don't know what it's doing, I'll say print something. Technically, you're supposed to set up breakpoints, but that's a pain. Um, but yeah, just take a look at this print stuff if you're new to Python. That's all. Okay, so I want to get to our first kind of like, I don't know what I call like computational physics problem, I guess. So we're going to use some of these ideas from built-in Python data types to study stochastic processes, which is something that is very related to the work I do on nonlinear dynamics, and I think it's kind of a cool topic from StatMech. Okay, so this is a notebook, right? So I've switched to a different notebook. So the first thing I have to do is I have to run my imports. So this all this junk, we're going to learn about this at a later point, but this is stuff I have to, this is external libraries that I'm going to use in this notebook for all sorts of misdeeds. The most important was I'm importing a bunch of plotting utilities and stuff that's going to allow me to draw pretty pictures. Okay, so Python is an object-oriented language, and the most primitive object you're going to run into is going to be functions, which Python formally treats as equivalent to any other object. So we're going to use Python objects to implement a stochastic process known as an Ornstein-Uhlenbeck process. So I wanted to draw a diagram of this, but my illustrator was broken, so I wasn't able to put it in there. So an Ornstein-Uhlenbeck process, wow, this person's really nice handwriting. An Ornstein-Uhlenbeck process, all it is I have some quadratic potential. So this is x, and we're going to call this v of x, where this is some energy function. And all an Ornstein-Uhlenbeck process is that I drop a particle at the bottom of that potential. That particle experiences random thermal fluctuations, so it sort of jostles around. And so basically it's the generalization of like a harmonic oscillator where now I have noise, so I'm going to like wander around. And I still have a force that pushes me back in, right, because I'm creating the potential. But what kicks me off the bottom is the fact that I have Brownian motion overlaid on top of this confining potential. Okay, so this is a stochastic process with a confining potential, whereas Brownian motion, you have no confinement, you just kind of wander around or something. So the notation I'm using is from stochastic calculus or whatever. It's not particularly interesting, but I'm going to say that dxt, so the dx here is the increment or the change in my particle's position over time. Its motion is going to be a combination of the restoring force from the confining potential, right? So the fact I have this harmonic potential squeezing me in is all this first term does. So alpha is just our spring constant, right? If that's a really big number, I'm really squeezed towards the middle more. And then this term is going to be our stochastic process. So this is why I use this weird notation, because stochastic processes, you write this sort of random jostling as this additional term dw. And this would look a lot more familiar, right, if I took this dt and divided through, because I would have x dot equals confining force. The problem is that in stochastic processes, usually this term is not differentiable, so you can't just take a time derivative and call it a day. And that's because this is basically like a random number generator, just is kicking your particle in random directions. And if I zoom in, I just get more random jostles. So the actual random forcing term is a non-differentiable function, which is its own sort of adventure in mathematics. But for our purposes, just imagine this is like, this kicks the particle in a random direction along the x-axis. This term squeezes it toward the origin, and these two terms compete with each other. If alpha is super tiny, basically I have random motion, I'll just wander around. And if sigma is super big, or if alpha is really big, basically this term gets washed out, and I just go to the origin. It's basically like I have no forcing, and it's just the simple overdamped oscillator or something. Okay, so that's like the fancy stochastic calculus way of writing the process. But if we actually want to simulate this, we're just going to write this in discrete time. So the discrete time version of this process is that the next position of the particle is its current position minus a contribution from the confining harmonic term, plus a contribution that's going to be essentially adding a random number to the position. So without this term, it would just be squeezed towards the origin. And this term basically adds my little random jostle that kicks it. I'm going to go ahead and close this door just because of the through traffic. Okay, so this is a discrete time simulation of this process. And for the purposes of just simplifying the notation, usually when you simulate stochastic process, you have to scale your noise amplitude by how long between when you observe it. That's just because if I wait longer before observing a stochastic process, those random numbers add up more. Just to make things way simpler, I'm going to set delta t equals to 1. So that goes to 1. Square root of 1 is 1. And so this is going to be a lot simpler to if we just work in units where delta t equals 1. I have a typo there. That should be a big delta. Um, and then the actual forcing function is just going to be a random normally distributed variable. So this is going to be a random kick in Brownian motion that they talk about all the time in StatMech. Okay, so we're going to implement this using a Python function. So this is the syntax for Python functions. You declare your definition, and everything within the scope of the function is indented. And then this is called a doc string. And this is just where I write about the thing so that then when I call help on this function, I can learn something about what I intend the function to do. So this is my documentation string or doc string. And this is the actual logic of the function contained with this scope. Okay. So there's a couple of details of how I've done this that are a little bit different than MATLAB. So just like MATLAB or C, I have a normal variable that's passed. This is going to be the current state of the process or the current position of the particle. So this is going to be X or like where I am. And then I have two additional things that have this specific syntax where I have the variable name equals something. So this is going to be where I implement this alpha versus sigma dichotomy, right? So the like random jostling amplitude versus the confinement. And rather than just have those be normal arguments, they're what we call in Python keyword arguments. And that means that they basically are arguments that have a default value. So if I call this function and I don't specify these two variables, it will implicitly assume alpha is 0.1, sigma is 1. And that's super useful to have defaults because when you get to like deep Python lore, you're going to find functions that have dozens of keyword arguments. And you don't want to have to type those all out if you just want to use the defaults. And so this is going to allow you to really use the same notation to have a function that has a lot of different things that it can do depending on changes to keyword arguments. Okay, so keyword arguments are basically defaults in other languages. Yeah, and I think MATLAB has syntax for this, but it's a little bit different. So just if you're coming from MATLAB, this is how we do defaults. This is one way of writing a function. And then another way you'll see me do this sometimes, this is kind of painful, but I don't know, I think it's cool that you can do it, is sometimes you'll see people use what's called lambda functions. And this is basically a way to compress all this nice fancy notation into a one-liner. And basically, this basically sets a variable to a function where lambda tells Python to treat whatever is after this as a special term. This is the arguments. I can still have keyword arguments, and then I implement the actual logic as a single line. This can be useful if you have like really simple functions that do basically one thing. Here, it's a little bit much to do this all in one line, but I just wanted to show it. And perhaps more importantly, lambda is special in Python, so don't use this as a variable name because it'll cause really strange behaviors because lambda is reserved by the Python language to denote one-line functions. Okay, so this is my process, and you can see from the logic here that all I'm doing is I'm separating it into where X is my current state. My first line does the confining term, so I call it the drift term by convention. My second line does this actual second step where I add the random noise proportional to sigma, which is this amplitude. And then my last line just combines current state, forcing, diffusion all together, and then returns the next value. So this will give you your current state and give you the next state of the stochastic process. Okay, so that implements one step of a process. So I want to simulate this for a super, super long time to see where I end up. So here I'm going to use a for loop where I initialize my particle at 0. Then at every step of this loop, I'm going to append the next value of the process as produced by my function. So just thinking through the logic here, all steps starts out initialized at 0. -1 pulls the last value from the list. So when we, on the first hit through this loop, the last value is 0 because that's where I initialized at. Then I'm calling this function. I'm updating the keyword arguments. I'm overriding them with these values. So then we go into the function. It takes this last value starting at 0. It uses these values instead of the defaults. It implements this logic and it spits out a new value. And that then gets appended to this list. And so this list grows in length over time. But every time I look at the list, I look at the last value, which is the most recent value of the process. So this one line combines appending to lists, it combines the slicing notation, and it combines the functions. And this is the sorts of combinations of Python things that we'll use in this class. Okay, so these two things together, when I run them, it's going to call this function 400 times every time using the last value, and this should simulate our stochastic process over time. So let's go ahead and make sure that everything's working. Yeah, it runs super fast. So this is what an Ornstein-Uhlenbeck process looks like when you actually run it over time. And I should probably do plot.x label. Great. Um, I don't know why they're not showing up. Um, okay. So that's an Ornstein-Uhlenbeck process. Oh, it's because my kernel's dead. Okay. Hmm. There we go. Okay. Okay, so there's my Ornstein-Uhlenbeck process, 400 steps because this loop has 400 units that's incrementing through. Okay, so first I'll talk a little bit about scope. So I mentioned that that white space in Python means something. So the fact that this is indented implicitly defines the scope. So here I defined the first term in the forcing as drift. So if I go and I try to like call out what that term is, it's not defined. I'll get an error because it's contained within the function. So you have private scope within Python functions, just like you do in Java and C. However, I can, if I want help with my process, I could do something like help. What did I call this? I call this an Ornstein-Uhlenbeck process. I can always do help Ornstein-Uhlenbeck process, and that returns the doc string of the function. So I'll get rid of my Lambda function because it's gratuitous, but here I took the time to write out this nice little description of what it does. So if I call help on that, it'll just spit out whatever I wrote. That might seem redundant because you saw me write that, but for some function that you're importing from some weird external library, you're not going to know the doc strings offhand. So you're going to use help in order to see whatever that function does. Okay, so that's a for loop using this Ornstein-Uhlenbeck function I defined, which just updates the state of the process once based off the most recent value. Okay, so just like in other languages, you can also define while loops, which instead of terminating after a fixed number of iterations, they terminate on a condition. We're about to use this to do something non-trivial, which is why I mentioned it. So if I wanted to repeat that simulation where instead of running for 400 steps, I run it until X gets at least 3 units away from the origin, I could do that by just setting a while condition here. So here I have my same for loop, but now it's going to run until it hits this condition. So what that means is that my particle over time is like doing random kicks, but if it hits, let's call that 3, call that -3. If it happens to wander and get over here, it'll kill the process and will stop. And we're about to use this for a bunch of shenanigans, so I'm just going to point that out. So this is going to be like, it's technically called a halting process, where it's an Ornstein-Uhlenbeck process until it hits +or-3. And the logic there is encoded with this absolute value condition here. So it's just a normal while loop like you see in other languages. Okay. So that's basics of Python functions, as well as sort of a basic implementation of Ornstein-Uhlenbeck. So we're going to use all those pieces and put them together to do something that I think is maybe a little bit non-trivial, that I think is kind of cool. So does all this sort of make sense so far, what we're doing? Okay. So we just defined this. So we just defined this combination of things where we ran a process once, and then you saw I use this while loop condition to basically run it until it hit one of these rails, and I stopped. And it looks like it ran for like, I don't know, 9 time steps before it hit a rail. That is maybe a hint that my confining potential isn't that strong, because I have this confining potential, but if particles are easily making it out to 3, obviously I'm not really confined that strongly, right? So there's some basic intuition there that it's terminating early because it's easy to get away from the origin because I don't have that much spring constant. So we're going to try to quantify that by taking that simulation I just did, right, where I ran this for, until it terminated, and I'm going to run that 1,000 times. So this loop isn't a loop over time. It's a loop over replicates, where I'm just going to do the same thing I just did a bunch of times, but every time I'm going to record how long it took before it hit one of those rails and killed my process. And so when I run that, and hopefully I didn't break anything this time, great. I'll get a distribution of count, where count is the number of replicate simulations, and then this axis is how many time steps they took before they hit +or-3. So this is a storied distribution in physics called the first passage time distribution. And this is a very fundamental concept, especially in biology and stochastic processes. It describes all sorts of things. For example, oftentimes I have chemical reactions that they only occur when I hit a very specific temperature. And so something like the first passage time distribution might tell you how long you expect to wait for my chemicals to hit that characteristic temperature, especially if I have thermal fluctuations. So this is a quantity. There's a whole book about it by Sid Redner. That is kind of a very useful thing to think about whenever you're dealing with stochastic processes, particularly the average behavior over many instantiations of the process. And we got there just by taking this while loop, running a bunch of times, and just bookkeeping how long each one took. Okay, so that's the first passage time distribution. So just keep that idea in mind because we're going to use this idea and kind of expand upon it a bunch throughout the lecture notebook. Okay, so before we play around more with that, one thing that I want to emphasize about Python functions is that Python is totally agnostic about functions other than they're just another variable in the interpreter. So what I mean by that is that if I define a function, I have all this fancy syntax, I use lambda, I use def, it all looks great. But as far as Python is concerned, that's the same as having an x equals 1.0. It's just now x equals a function or something. And so Python treats functions on the same level as any other variable, meaning that you can kind of do weird things with functions in Python that aren't always as easy to do in other languages. So just to give an idea of that, here I'm going to use my lambda notation just because I wanted to be lazy with typing to define two first passage processes, and one of them is going to have a really really small spring constant. I'm going to call this a wide process, and the other is going to have a bigger spring constant, so it's going to have a more strongly confining potential. And we have this naive expectation that the process should be squeezed in more if I have this bigger spring constant here. And then while I'm at it, I'm going to define two other stochastic processes. I'm going to define a process with no confinement, so that's just a Wiener process. And then I'm just going to define a process that's essentially is essentially a random value generating process. It's essentially a random walk, or the step length of a random walk over time. So these are all just condensed notation that I'm given a position and it spits out a new position where the actual physics differs depending on which process I'm simulating. So every one of these variables is a function. But as far as Python cares, it's just another variable that happens to store this logic that can implement iteration of new values. Okay, so I'm going to take all this like code I did here, and I'm going to wrap it inside a function called first passage time that takes a function as its first argument. So this is I think the first weird Python thing that you'll see, which is that this is the same syntax as any other function, right? It takes some variables, has some keyword arguments and all that. I'm going to call my guardrail a keyword argument, but I'm going to keep it set at 3. But now I'm actually going to pass it the stochastic process as a variable. So I defined 4 up here, right? 4 different stochastic processes. All this logic is the exact same as we saw before, but now it's going to be able to take whatever stochastic process I specify by passing that variable. So let's make sure that's in scope in my notebook. So let's run that. Looks good. And once again, I'm calling this help function, which allows it to spit out the syntax here. So I can read my doc string if I was given this function without the actual definition. Yeah, what's up?
So is it actually like a good practice to have like pass this function as a argument to another function? Because if you could just define 2 functions, can't you call one function another function?
So it can come in really handy. Like an example where I see this come up a lot is there's a lot of like machine learning techniques that operate essentially on distance matrices. So like I have a bunch of data points, I find all pairwise distances between them or something like that. And most of the time we use L2 distances, like Euclidean distances between all data points, but a ton of scikit-learn functions allow you to pass a custom metric. So you can basically pass a function to it that will do whatever pairwise operation you want. And so without the maintainers having to know anything about, I don't know, L1 distances or like Chebyshev distances or whatever, I can just pass a function that implements whatever crazy thing and get a distance matrix. So I do see passing of functions even in like modern code, but I agree it's not the most elegant thing because it's so Python specific, but it does pop up. Okay, so I just defined this function that takes a function. So just to complete the loop, I'm just going to take all these different first passage time processes I just defined. I'm going to run them, and I'm going to hit an error because I didn't run my cell. Okay. Okay, there we go. Every time you close a notebook, you should know that it wipes all your local variables, so you have to rerun everything. So just notebooks are kind of special in Python because they have local scope to the notebook, but when you close them, the local scope gets wiped. So just as you just saw, watch out for that. Okay, so all I'm doing is I'm just running this first passage time function on these different stochastic processes, and I'm going to focus first on the wide versus the tight process, so without the different confining potentials. And I'm going to plot the first passage times on a vertical log plot. So the vertical axis has logarithmic scale. Okay, and I'm showing them on the same axis so you can really see what goes on here, which is this looks suspiciously like a straight line. Okay, so if you look at it, right, like this is the type process has this really long, this really sort of wide distribution. The wide process has this very narrow distribution. And this corresponds to, how many of these simulations took however many time steps to get out here. Uh, so at first blush, I think that this seems a little unintuitive, right? Because this is actually the process with a higher spring constant, right? This process is more tightly confined, but it actually has a wider distribution. And this is sort of the confusing thing about first passage time processes, because if I were to draw the distribution of particles for the tighter process, it would actually be narrower, right? Because I have the confinement. However, as a consequence of that narrowness, it actually takes way, way longer for particles to diffuse out and hit these extreme values at plus or minus 3. And that's because they're getting pulled back to the origin so strongly. So the tighter process actually has a wider first passage time distribution. It's almost like, I think it's a little much to call them adjoints, but there's sort of this natural sort of inverse or transpose like structure to the two processes, which is part of what makes first passage time processes kind of an interesting physical phenomenon. And then conversely, like my wide process is barely confined, so the particles find their way to plus or minus 3 super fast. That's a really small distribution. So this is, we're doing for loops and sort of simple logic, but this is an example of a pretty non-trivial result that this is an exponential distribution that is enabled just by kind of combining these different Python operators together. Okay, so that's just different, Ornstein-Uhlenbeck processes with confinement. So just to sort of complete the loop, this is my random walk process, and this is my Wiener process. And you can see they still have this sort of linear-like decay on this logarithmic axis. So it looks like a lot of these first passage time processes have exponential tails. And that's actually a pretty major idea in first passage time processes, which is that for those of you who are big fans of the lore, first passage time processes are often represented in Laplace transform space, which is the space of projection onto monotonically decreasing exponentials. So this exponential structure here shows up just when I run a bunch of for loops. I can see that there's something popping out here. Okay, so that's first passage times of an Ornstein-Uhlenbeck stochastic process. So just because this was bothering me, I was curious if there was a simple way to prove that the Ornstein-Uhlenbeck process has a linear or has an exponential decay in its first passage time. You actually can prove it. This took me a bit of time to figure out. I'm going to highlight a few things from this, but this isn't StatMech, so I'm not going to like go crazy on this. Okay, but I do think this is cool, so I might just show you this. So this is just my definition of my Ornstein-Uhlenbeck process, right? It has this funny notation, but basically this is just a differential equation. So even though this isn't a real differential equation, I can still act like it is and solve it using integrating factors. So normally if I had like a dx dt equals some junk plus some other junk, I would use integrating factors. The only thing that you get that's weird with stochastic processes is you get an integral over the process, which is its own lore. And this has an interpretation in terms of it's called Ito's interpretation of the stochastic process. But importantly, like if you just saw this, you say, oh, he used an integrating factor to solve that, right? And that's all you really need to care about for now. So I can actually analytically solve for the position of the particle as a function of time as a function of its initial position. We're just using 0, but you could put something else there, plus this integral over the random values of that noise term. And you'll notice that alpha shows up here as a weighting factor, which again looks suspiciously like a Laplace transform. Okay, so that defines x as a function of t. So if I define the first passage time, that just corresponds to the lowest value of t infinitum. I don't know, maybe that's pretentious to write it that way, such that x first crosses that boundary at xc. Okay, so in order to study an ensemble of these, we're going to pull right into StatMech, and we're going to take the dynamics of a single particle, and we're going to instead transform it to the dynamics of an ensemble of particles. And this is going to be using the Fokker-Planck equation, which some of you guys might have encountered before in StatMech. And the Fokker-Planck equation is the way you go between talking about motions of single particles to talking about what a big distribution of millions of particles does. It gives you a probability distribution over time. So this derivation, it's in the Van Kampen book and a bunch of other sources, but basically there's some principled way you can take the dynamics of a single particle in harmonic confinement with Brownian noise and convert it to a PDE that describes the probability distribution across the x-axis, so just the distribution of particles, as a function of the drift term, so this is your confinement term, and the diffusion due to the actual Brownian motion term. And this is just a PDE that describes what happens to the distribution instead of single particles. And this derivation is its own thing, but importantly, you can see alpha appears on this term, and my noise amplitude appears on the second term, and this PDE is well defined. Okay, so the question is, can I solve this PDE to actually guess what my distribution of millions of particles, the ones I'm simulating, will do over time, even though my simulations are focusing on single X's, but my PDE describes an ensemble. Okay, so when I ran these simulations, it looks like there's some well-defined statistical structure. So what I'm going to do is I'm just going to run my Ornstein-Uhlenbeck process. So I have the wide and I have the narrow ones. I'm just going to run this for a bunch of different trajectories to see if I can tease out what this ensemble is doing. So hopefully everything's still in scope. It is. Okay, so this is just like, I think I have 10 here, Ornstein-Uhlenbeck processes. They like to stay near the origin because of the confinement, so they don't wander off to infinity. They look kind of crazy or whatever. So here I'm running 10,000 of them, and I've changed the transparency. And you can see that even though each process is doing its own crazy thing, there's pretty well-defined ensemble structure here. And in fact, if I just take a cross-section, so I just take a histogram of where all the processes are at time t equals 200, this sure looks like a Gaussian to me, right? So even if I don't know anything about stochastic processes or I don't care or whatever, I might still look at this and be like, maybe P of X of t is a Gaussian. So this tells me that there might be some well-defined statistical structure that I could use to narrow my problem domain. So we can go ahead and exploit that to make progress on this Fokker-Planck equation. So what I'm going to do is I have this equation. We've been given to it by some very talented textbook writer like Van Kampen. We want to solve it, but I have no idea how to solve that a priori. So I'm going to do everyone's favorite trick and use the fact that I guessed the answer to try to solve it retroactively. So I'm going to go ahead and guess that P is a Gaussian distribution because it sure looks like one here. So I'm going to insert a Gaussian, and we know that the center of the Gaussian is probably a 0. That makes sense because there's a symmetry in this problem, so it would be really weird if that wasn't the case. But just for fun, we're going to assume that the variance of this distribution is a function of time initially. So we're going to leave that as a time-varying variable. So this is just a Gaussian with a time-varying variance. And you can probably guess what's going to happen here because it sure looks stationary. But let's just see if we can prove it. So I'm going to take this ansatz. I'm going to plug it into my actual Fokker-Planck equation. And if you plug and chug with this distribution, you'll actually get out an ordinary differential equation. And I'll just mention that my boundary condition for my simulations, so I'm starting out a bunch of points at the origin and I'm letting them diffuse. So my initial condition is really just a delta function at the origin for that PDE. That's important because I can't actually solve anything unless I specify that. But when I actually substitute in my ansatz, I actually get an ordinary differential equation for the variance as a function of time. So I plug and chug, all of my x dependence drops out, and I just get a function for the variance over time. And you can actually solve this ordinary differential equation to get what big sigma as a function of time is. In this ordinary differential equation, so I say I start at a delta function because all my trajectories are at the origin. So that variance is 0, right? Or in a limiting case, it's 0. So I plug in that initial condition, I solve, and I get this analytic expression for the variance of a distribution of particles undergoing motion in an Ornstein-Uhlenbeck confinement. And this is kind of cool because what does this tell us? It tells us that I have some constant term here that is proportional to the noise. That makes sense because I have a lot of crazy jostling. I expect there to be a wider distribution. But if a tighter distribution, it should be narrower. So those two compete with each other by being proportional to variance and inverse proportional to the spring constant. But then I have a transient, this term that's 1 minus e to something that depends on time. So that tells me is that once enough time has passed, this term gets super tiny, and I basically just have a constant asymptotic variance that's constant. So what is that telling me? That's telling me basically what I'm seeing here, which is after some time has passed, I basically just have a steady state Gaussian distribution. So even though I have these two competing forces, they balance out and I just get this nice stationary distribution. And in fact, the units of time there is going to be 1 over 2 alpha. And so if I write that for my process, for the tighter process, the high spring constant, after one simulation step, I've already thermalized. And even for the other one where I had 0.05, so it was a less stiff process, after basically 10 time steps, I should have reached this equilibrium. And that makes sense because you can basically see here that after 10 time steps, I'm done. So you can basically, so in other words, like we just started with a bunch of for loops, but we actually got a pretty non-trivial result here. Like reasonable minds will differ, but I think that this Van Kampen derivation is actually kind of like a graduate level result in first passage times, but you can basically just see it in your simulation with a bunch of for loops, which I think is kind of cool. Okay, so I ran out of steam on this, but you could even take this a step further and use this distribution to even prove why this is an exponential distribution. We're going to leave that as an exercise to the reader because it's actually really nasty. But the idea is that if I'm sampling points from a Gaussian distribution over time, the question is how often do I hit extreme values if I'm just sampling a statistically stationary distribution? That has to do with binomial processes, which you might have seen before, I think in StatMech. The continuous time limit of a binomial process is an exponential distribution, which is where that comes from. I just skipped a bunch of steps there, but if you're interested, there's a way to take this one term, plug in some sort of stats type stuff, and derive this exponential term analytically. So you can basically get the leading order behavior of a first passage time process just by doing the simulation, getting an ansatz, and plugging it into your analytic work, which I think is pretty crazy. And if you want to play around with that, I put some questions here or something. Okay, and here I was playing around with my analytic solution. Okay, so that's first passage times, and that's also the first taste of using functions in Python. So I don't have I'm a little short on time, so I'm not going to go super crazy into this, but I want to give you a preview because it's interesting. So this idea of passing functions to functions is, I don't know, it's a little janky, right? It's kind of confusing notation. So most of the really, really good Python code you'll find is going to use a very different convention that's unique to Python and other object-oriented languages. And it's going to be called classes in Python, but it's really just objects. And the idea behind classes is that we're going to take all of the logic that we just implemented. First, we define the process, then we define the simulation of the process, then we define the first passage time, and we're going to wrap it in a single object where each of these different things we wanted to do is accessible within that one bundle. So you can think of classes as like big bundles of functions and variables and other stuff we care about, that's all contained within a single scope. And I think I'll briefly get into this either Friday or Monday or whenever. But just to give you an idea of what that notation looks like, classes in Python always start with a constructor. That's going to be this special init method. And whenever I define the constructor of a process, I'm going to pass it variables that basically define the sort of intrinsic properties of that process. So for example, in Ornstein-Uhlenbeck, I have the entropic force, right, the jostling, I have the confinement force. Those were two numbers I cared about. So when I define the process, I'm going to set those as variables that are locked to the class. That's what this self dot does. It says that these two things are intrinsic properties of my process. And then when I call the object and I initialize it, those are going to be set as properties of this process. Once I've done that, the object just exists in memory. It has these two variables bound to it. And then I can define methods that take the internal state of the object and perform operations. So my single step process function that I defined above that just incremented by once, I'm going to call that step. This is a notation you'll see in a lot of other classes we'll see. This does a single loop or a single run of the process. And then I'm going to have another method that actually does, like a million loops of the process or something. So I'm going to split that logic into two separate functions that are all within the scope of the class. And in the context of objects, these are called methods. So this single object, after I define it, is going to have tied to it parameter values, but it's also going to have functions tied into it. And those functions can see these internal parameter values without me specifying them. So the notation for that is going to be instantiating the object. So here I define my Ornstein-Uhlenbeck process with this stiffness and this sort of entropic force. And then if I actually want to do stuff with that object where I fix the physical parameters, then I'm going to use these internal functions like run process. This calls this object I just created, but the object already knows what the stiffness and the variance is because I defined it as properties of the object. So when I actually call this function, it's going to say, oh, I want to run this for 400 steps, but it's going to use the internal values that are tied to the object. And this seems a bit indirect, but this is super critical for stuff like numerical integration, where I'm going to define my simulation. Maybe I have some like weird, I don't know, chaotic system or something. And you're going to think of these as something like the parameters of your differential equation. And then these are going to be in the things that actually implement things like your simulation or your time stepping or whatever. So being able to sort of bundle your parameters and your methods into one object and thinking of that object as sort of the Python representation of a mathematical object, that's going to be really powerful. And that's something that we're going to exploit quite a bit when we do stuff like inheritance and all that. Yeah. And so, if you're new to object-oriented programming, I'd encourage you to just take a little bit of a look at that. But in the next class, we'll talk about how you can then go even further and daisy chain objects together to get even more general constructions in Python. Thank you.